Hey, what's up, Chem Peeps? What in the heck are we gonna do in this vid? We are going to distinguish between unsaturated, saturated, and supersaturated solutions and investigate factors that influence solubilities. Breaking it down as always, we are going to 1. Distinguish among saturated, unsaturated, and supersaturated solutions. 2. Define solubility. 3. Interpret solubility graphs. And 4. Compare the effects of temperature and pressure on solubility. Alright, so let's get this party started. When we talk about solubility of a substance, we're talking about the amount of that substance that's required to form what's called a saturated solution with a specific amount of the solvent at a specific temperature. So, some terms to keep in mind. When we talk about a saturated solution, we're talking about a solution that contains the maximum amount of dissolved solute. Take a look at this thriller of an animation from my good friends over at FET. Got a 1 liter beaker of pure water, my solvent, and my solute that I'm going to add to it, potassium dichromate. As I add my solute to the water, making a solution of potassium dichromate, notice that the solution gets more and more concentrated until I hit a point at which the solution can hold no more solute. Doesn't matter how much more I add, it's all gonna end up sitting on the bottom of this beaker. Because I've saturated this solution, it's holding the maximum amount of solute that it can at this temperature. An unsaturated solution, then, is a solution that contains less solute than a saturated solution under the same conditions. So if we come back to this thriller of a simulation, if I were to say remove a bunch of my solute to the point where I don't see any solid sitting at the bottom, I know that that solution can hold more. And we would say that this solution is unsaturated. Now, here's an exciting image that shows you the difference between an unsaturated solution of sodium chloride and a saturated solution of sodium chloride. Side by side. Notice in the first example, we start with 30 grams of sodium chloride and 100 mils of water. Add the two together, completely dissolves the sodium chloride, no solid remains, the solution is unsaturated. It could potentially hold more sodium chloride. But right beneath that, if we started with 40 grams of sodium chloride and added it to a new 100 mils of water, it would only dissolve 36 grams of that, completely saturating the solution, and the excess solute would just hang out at the bottom undissolved. Now, in addition to saturated and unsaturated solutions, it's important to be aware of supersaturated solutions. And these are solutions that contain more dissolved solute than a saturated solution under the same conditions. Now, I know that can be a little confusing, so let's come back to this image. We've got an unsaturated solution of sodium chloride at 25 degrees Celsius, a saturated solution of sodium chloride at 25 degrees Celsius, but in order to create a supersaturated solution of sodium chloride at 25 degrees Celsius, we would have to take that saturated solution, heat it up until the remaining 4 grams dissolves, and then slowly cool it back down to 25 degrees Celsius. What results then is what we call a supersaturated solution. It is holding more solute at 25 degrees Celsius than it should. Remember, it should only be able to hold 36 grams. And keep in mind that supersaturated solutions are very unstable. If you were to knock that beaker, or if a fleck of extra sodium chloride were to fall into solution, you would immediately return to the saturated solution, while that extra sodium chloride would fall out. But our focus is going to be on saturated versus unsaturated solutions. And if you take a look at your notes and on your screen, many times you're going to be interpreting what are known as solubility graphs to determine how much solute can be dissolved in a certain amount of water at a given temperature. You've got a solubility graph for a bunch of different solid salts in water, and also you're given a graph of the solubility of different gases in water at different temperatures. Now, how do you interpret these graphs? Well, simply realize that the line on the graph indicates the point at which you have saturated that solution at that given temperature. So, as an example, let's take a look at this green line that represents potassium nitrate. At 10 degrees Celsius, 100 grams of water can only hold about 20 grams of potassium nitrate. But if I heat up my solvent to 40 degrees Celsius, that 100 grams of water can now hold a little over 60 grams of solute. So this line indicates the maximum amount of solute that you can dissolve per a certain amount of water at a given temperature. In other words, it indicates the solubility of that substance at different temperatures. Now, if you are looking at your graph and you're at any point below that line at a given temperature, that would indicate an unsaturated solution. Any point above that line, however, is going to indicate a saturated solution, but one that contains excess or undissolved solute equal to the difference between the point above the line until the point on the line at a given temperature. So let's come back to this graph and once again take a look at potassium nitrate. Let's imagine the temperature of my water was 40 degrees Celsius and I only placed 50 grams of potassium nitrate in that 100 grams of water. The solution would be considered unsaturated because at 40 degrees Celsius, that 100 grams of water could hold more potassium nitrate. However, now let's imagine at 40 degrees Celsius that we've placed 80 grams of potassium nitrate into that 100 grams of water. The solution is still saturated at any point above the line, except now we've got about 15 to 20 grams of potassium nitrate that has fallen out of solution and is sitting at the bottom of your beaker or container. Same thing applies to gases, except just recognize that when we're talking about gases, they're not going to settle out at the bottom, they're just going to exit the solution. All right, finally, let's talk about a couple of factors that will affect the solubility of solids and gases in solution. Okay, so let's first talk about pressure. Pressure will affect the solubility of gases in liquids. Generally speaking, if you increase the pressure, you're going to increase the solubility of a gas. Think about your sodas or your pops. You shove a bunch of carbon dioxide under high pressure, and then you crack open that can or twist open that bottle. The decrease in pressure releases a bunch of gas. The gas comes out of solution. The second factor you want to think about is temperature, and this will affect both the solubility of gases and solids in liquids. In general, an increase in temperature will decrease the solubility of a gas. Now, as you think about why, take a look at this animation that's going to continue to repeat on your screen. Notice that at the lower temperatures, we're able to get more gas dissolved in solution. But when we increase the temperature, more of that gas is going to come out of solution. And let's think about why. When you increase the temperature, you're increasing the kinetic energy. And the more kinetic energy that those particles have, the more likely they are to overcome the intermolecular attractions between the water molecules and those gas particles. And so the gas particles are able to escape. So again, come back to this solubility graph for gases. Notice that as temperature increases, the solubility of gases will decrease. And then finally, when we're talking about solids, an increase in temperature will usually increase the solubility of a solid. Again, take a look at this solubility graph. For the most part, the hotter you get the solvent, the more solute it's able to dissolve. All right, that does it for this video. Have a fantastic day.